Uh-oh. Oh, that's gonna, okay. That's gonna loop. Alright, that one concurrent viewer thing is me. Nice. Alright, so the goal is to, can I not? Oh, okay. Let's try that again. Let's try that one again. Okay. Alright, so, welcome. Hello, hello. Guten Abend. Good evening. Good day. So what I wanted to get into is put another hour in here, and I'm slowly working my way through these problems. It's good. I don't know what I'm going to do. Oh, I have kind of an idea what I'm going to do after we're done here. Yeah, learning Clojure, finagling with Clojure. I think it's pretty neat. I like Clojure. I like it. Yeah. Just keep on going, keep studying. There's lots of stuff to learn and to work with and to do. The thing we're going to get into next is machine learning, I think. Well, we'll do two things. One, we'll do some like website building. We're going to build ourselves a little small website with Clojure script, Clojure backend, Clojure server, and or Clojure backend with a Clojure server and Clojure script for the front end. We'll just build like a small website on a machine that I have purchased. Kind of walk through that, how that's done. I was thinking I could solve all the hard problems on LeetCode, and also the hard problems on HackerRank. That may not be such a bad idea, because apparently those gain views on the internet, on YouTube's. It's been like slowly growing those videos, so that's kind of cool. It's kind of neat. I was thinking that may not be a bad idea also. There's a few things I want to do. There's a bunch of stuff to do. Many things, them things. Slowly but surely, we'll just step at a time here. Go slow. Yeah, so let's work on the food that's in front of us here, right? Let's chew the bite we got in our mouth right now. And by that I mean let's continue. So I'll just explain the solutions to the previous problems. So here we've got, just refresh this. Graph tour, hard graph theory. Starting with a graph, you must write a function that returns true if it is possible to make a tour of the graph in which every edge is visited exactly once. The graph is represented by a vector of tuples. Each tuple represents a single edge. The rules are, you can start at any node, must visit each node exactly once. All edges are undirected. So this is what's called an Eulerian tour, and I have Eulerian path, and Eulerian path, Eulerian cycle. Now, there was some mistake I made originally. What it comes down to is you build your adjacency graph, and then you can Eulerian paths, whether or not a set of points has an Eulerian path is a lot easier than a Hamiltonian path. So an Eulerian path, which we saw Hamiltonian previously, Eulerian path, what is it? Has if and only if exactly 0 or 2 vertices have odd degree, and all of its vertices belong to a single. Yeah. So trail if and only if exactly 0 or 2 have odd degree. Yeah. So is that what we did? We do that properly? 0 or 2. Yeah. Did I do this right? Now, there's a few solutions to this. I'm not going to go over them, but I'll just explain how I did it. So I made a symmetric closure over the relation set, or the relation, the binary relation. Created an adjacency map out of that symmetric closure. Checked. I used a depth first search type of thing to check if it's connected. And by just counting the nodes, right? If the number of nodes you count while traversing through the depth first search is exactly the size of the set, then obviously it's connected. Then I said, okay, is there a tour that exists that says exactly 1 or 0 or 2 vertices of the odd degree, as per probably Euler himself found this result. I don't know who did, but yeah. So it's not trivial, but it's simple to check, easy to check, and that's it. So I just check, take that edge set, create a closure, create an adjacency map, check if it's connected, and then that it has an Eulerian tour, and that's it, done. And the way you check that, you just take from your adjacency map, which is pretty simple, right? It starts with a map, reduces using a reduction that associates at each step with whatever is at that key. If there's nothing at that key, you take an empty vector. If there is something, then you just append B to it, where B is where the edge is pointing. And that's how you create the adjacency matrix. And then how do you check this? You just take vals, are the basically is the degree. The vectors, the size of the vectors of vals of this hash map is the degree of each node, and you can just take the count of the number of odd ones. Check if that odd number is 0 or 2. That's it. Pretty simple. All right, I don't want to spend too much time on these. These are kind of easy. So I know it says hard. It's hard in Clojure maybe, but it's not really hard. It's a pretty easy question overall. Maybe hard if you're not familiar with Eulerian paths. I guess then it'd be hard. It'd be probably impossible if you're not familiar. It's probably impossible if you're not familiar. It'd be really hard. Yeah. Building that theory from scratch is like, yeah, it'll take you a while. That might take you a while. All right, let's go to 90. Cartesian product, guys, that's pretty easy too. Could just use a list comprehension over both of the given sets. They said just 2 sets for the Cartesian product, so you could do an arbitrary number of sets. It would be an arbitrary list comprehension, I guess. Although that's maybe a little bit harder to. You maybe want to use something that's like somehow recursive. A recursive list comprehension. I don't know. Don't exactly know what that would look like. I don't know. I'm actually not sure. An actual Cartesian product function is kind of interesting. It's like all combinations, not even combinations. It's like all permutations with replacement. It's sort of what it's like. It's pretty good. I like Cartesian products. They're useful to think about, but yeah, a function in Clojure that implements a Cartesian product, I don't actually know offhand. I mean, obviously you can use a list comprehension to do like sort of a variadic version, but even the list comprehensions themselves, there's certain, you kind of know, like what I mean is at compile time the size of your Cartesian product, if that makes sense. In other words, it's not like you could programmatically switch between the Cartesian product of 1 set and the Cartesian product of 2 sets, or Cartesian product of 3 sets, or arbitrary number of sets at runtime. Like, in other words, change the size of this. You know, whereas a Cartesian product function you would give a variadic. I don't think it's impossible to program such a thing. I think it's probably relatively easy if I thought about it some more. But offhand, it's kind of like, how would you do that exactly? It'd be some kind of like, what do they call that? Like, yeah, it's probably just like a backtracking algorithm type of deal, something like that. All these permutations without replacement over multiple sets, taking elements from multiple sets, or each sort of slot in the tuples that you return would be each element would come from another set. Yeah, anyway, so it's pretty easy in this instance because we could just employ the Cartesian product. All right, let's go to 91. Tomorrow we'll try to make more progress. Graph connectivity. Now this is kind of ironic because we already we already been employing the connectivity of the graph repeatedly in our other questions, other algorithms, but now they finally ask us for it explicitly. So here we go. Given a graph, determine whether the graph is connected. A connected graph is such that a path exists between any two given nodes. Your function must return true if the graph is connected and false otherwise. You will be given a set of tuples representing the edges of a graph, each member of a tuple being a vertex node in the graph. Each edge is undirected, can be traversed in either direction. Yeah. So let's do that. Excuse me. Same algorithm. Reductions, recursive reduction. Build the symmetric closure, build the adjacency. It's basically the same thing as the Eulerian Tor question, just don't implement the portion that calculates the Tor. Pretty much the same thing. Go through these kind of quick. Roman numerals. Now this was an interesting question. How I initially implemented it, I used so we'll read it first. So another quote unquote hard. Roman numerals are easy to recognize, but not everyone knows all the rules necessary to work with them. Write a function, parse a Roman numeral string, and return the number it represents. You can assume that the input will be well formed in uppercase and follow the quote unquote subtractive principle. You don't need to handle any numbers greater than MMM, CM, XCI, X 3999. The largest number representable with ordinary letters, right? So you got, this looks 14, this is 827, this is 3999, and this is 48. So the deal is, what I did initially was I wrote a very large regular expression, which would actually operate on the digits place. So it would isolate the thousands, then isolate the hundreds, then isolate the tens, and then isolate the units. And then each grouping that would be matched would then be, hold on a second. Map each grouping to a through a hash map to an integer, which represents, so the match regex would be clever enough where you could match sort of a few different pieces of these symbols. So obviously each set has 10 different sort of groups of symbols to match. Be clever enough not to have to match one symbol per I guess per sequence of 10, range of 10, In other words, it didn't just match, the regex wouldn't just match MMM and then MM and then M and then, well, there's only 3 for that one, but the other ones would be, like, what is this, CVL, I think, yeah, CM, right, matching, so there would start with, it'd be CM, then it would be DCCC, then DCC, then DC, then D, then L, no, then CD, then CCC, CC, and C, right? So like instead of writing a regex that matches each one of those 10 different groups individually, you know, I would throw in a few different regexes, like regex value operators. So you'd have like, for instance, the C would just be C plus, would capture all 3 of those different possibilities. Then the D, C possibilities, right? There's about D, DC, DCC, and DCCCC. There's 4 of them. So you just do DC with a asterisk, right? And could go that way, right? And you could do a similar thing for also the other classes where you have the other, that's for like the hundreds. You do a similar thing for the tens, a similar thing for the units. That was all well and good, and then I just filtered that into a hash map. That was all well and good. I learned a little bit about, you know, regex pattern matching. There's all kinds of neat things that have been added over the years that people put in there to make your regexes, extend regex functionality a little bit, which is cool. So that worked, but the problem is that it's a pretty big and ugly regex you need for that. And then it's also a very large table that you've got to use of like hashing, like in order to hash these values appropriately, you need, what did I say, there was like 5 or 6 different symbols for that range. So it comes out to something like 20 different groupings that you need to map numbers to, which is just kind of a lot of, oh no, excuse me, no, the regex doesn't need that many symbols, but when you actually map the thing, you ended up just mapping things directly. Which was kind of awkward and kind of, what's the word? I don't know, it was just kind of bulky, just kind of heavy way to do things. Or at least it was heavier than the alternative, which I'm going to show you now. Now there's a very clever way of doing this, approaching this problem, where you can say, okay, look, this subtract, we're going to, you know, in all cases, we're going to assume this is well formed, this expression. Now that's an interesting kind of caveat. If it's not well formed or if it is well formed, basically I don't think that the regex pattern that I wrote initially probably could be used to check if you have well formed, quote unquote well formed numerals. That may be useful. A hybrid of these 2 solutions I'm about to show you may be useful. But what you end up with is, assuming it's well formed, you can say, okay, the subtractive principle only applies when the value of the character we're looking at is less than the next character. So you can do a clever trick where you say, okay, if you ever see that, what you can do is map each of these symbols to their value in a vector, in a sequence, and then say, okay, if you ever see that, go ahead and swap the value that you see there in that sequence, in that vector, with its negation, a negative value, right? Like instead of adding I, you're going to subtract I if you see I and 5 or I and 9 and 10 or whatever you see. You could do that and end up with just a simple summation over all the values that you have left over. It creates a really nice, like simple solution, and that's what we have down here. I saw that in someone else. It was really someone else's solution, so I grabbed it and sort of more or less copied it. What I did was, what you do is you just zip map each of the letters with each of the their values, and then you replace using this map over S, which I didn't realize you could do that with the replace. You can actually give it a map, which is pretty cool. So it does a whole bunch of different replacements, I guess, in one shot. And so now you've got a sequence of numbers instead of numerals. And then you say, you perform this operation that I described. What you do is you take another map, and you take as input, you take the numbers and then the rest of the numbers as two different sequences, where the rest of the numbers, it just removes the first number, right? So this is sort of the first set of numbers, and then the set of numbers with the shifted over to the right, or shifted over to the left. Yeah, you can say however you want to think about it. Shifted over such that you're not looking at the first element anymore. You're looking at the second is in the front. And so what happens now is if you map this function over those two sequences, you're going to be comparing the first and the second and the third and the fourth, etc. And then you also just need to add an extra value here at the end. So I just put a copy of the last number there again. I'll explain why that has to happen and what that means. But then you perform this map over these two sequences of the same length, roughly the same length, and you just do the comparison directly and say, okay, if the first value is less than the second value, then we're going to return the negation of that value. Otherwise, you just return that value, and you construct a new sequence using this map, which I thought was pretty clever, pretty succinct, pretty clever. The reason for this concat at the end, the idea is because you shifted over you shifted over your values in the sequence, you don't have a last value. You have one less element. So what will happen when you perform this operation is you actually would otherwise end up losing the last value. The way the map works is it truncates. It only takes pairs of the first elements of the sets, then the second elements, etc., of the ith elements of the sets that you're interested in, up to the smallest size set. Up to the smallest. So itchy, man. Yeah, up to the smallest set. So like if you have one less element and you try to perform this operation, you're actually just not going to get a value for the last element. So you've got to add an element, and then we also want to guarantee that element simply returns whatever the last thing was. We don't want to negate it, obviously. So we would want to make sure that it's at least, whatever this thing we throw in there is at least, it's at least less than or equal to the last value of the sequence. And yeah, so we actually put that in there, right? So we use the last element for this. And yeah, so once you perform this operation, compared everything as required, you'll have some negations in there, which are everywhere you see that sort of smaller and then larger valued symbols, and then you just simply apply, simply add across all those numbers, and you're good to go. 92, done. Okay, let's go to 93. So yeah, I thought that was pretty nifty. That was like a very concise kind of solution. I thought that was good. I like that. I thought that was good. Phone needs to charge. I don't know if it's charging or not. Cannot tell. It charges, but then it's also on the light, so it's like losing juice while it's charging. It's not great. Write a function which will flatten any nested combination of sequential things, lists, vectors, etc., but maintains the lowest level of sequential items. Result, should be a sequence of sequences with only one level of nesting. Actually, my solution for this was kind of bad. I haven't really figured out a way to fix it up. There's a problem with it. It works, but we'll describe what the solution. Actually, maybe I can modify it while we're talking about it. So, let me think here. Wait a second. Let me try something here. Whew. Something like this. See what happens here. Expecting to get an error. No, really. There we go. Yeah. Oh, I guess it like optimized it out or something if I didn't print it. Right. So there's a reason for this. Thinking of a possible way to resolve it. So I'll explain what the problem is and what we did here and all that. Partially flatten a sequence, write a function which flattens any nested combination of sequential things, lists vectors, etc., but maintains the lowest level sequential items. The result should be a sequence of sequences with only one level of nesting. All right, so the way I solved it, we'll start with that. So I said partial flatten, write a set of sets predicate, which I'll explain in a moment, and then we're going to filter on the complement of that set of sets, and we're going to use a tree sequence, which is basically depth first search, or no, excuse me, it's a depth first search over tree. It's effectively depth first search over tree structure, and we're going to use this set of sets predicate to figure out whether or not it's an inner node or a leaf, and then we're also going to use the identity to find out what all of our leaves or children or leaves are going to be for any given node, and we're going to operate over this set of sets, we'll call it. Probably shouldn't use SS, I don't know, I could use just X, it's probably better. Because these aren't sets of things, these are collections of collections. It really shouldn't be a set of sets, it should be a collection of collections. I think now that we're going over the semantics of it. I fairly often mess up my, fairly consistently screw up my, just like the semantics of my solutions, you know, like there's probably better ways to name these things so people can understand it. Anyway, so the idea is, so this collection of collections just checks, given some X, it says, okay, is it true that there's some thing in X that has a collection in there, right? So if all you see in X are things that are sort of not collections, i.e. they just have, what do you call that? Well, things that aren't collections, you know, like integers or, I don't know, some kind of value, doubles, integers, whatever, something, some numerical expression, right? That would be sort of the lowest level, right? So you don't want to go lower than that. But if you have a collection somewhere in there, then you know that, oh, this thing is a collection of collections, so that you can sort of quote unquote reduce it. Now, actually, what I should do is collection of only collections, right? So the problem that we ran into is that if you execute this on something that has a collection in it, but also has something that's not a collection, the problem is that this tree sequence is going to try to operate on all of the children, which is the identity, which is just everything in that collection. And the issue you run into is you try to run this command on something that's a number, right? What happens immediately is you say, okay, I see a collection here, so this is a collection of collections. So let me now operate on the children, which is one of these is this child, and now let me execute this predicate again on that number, and then it says it's not a sequence, right? Which is a problem. So really what you want is everything here a collection of only collections. You say if every true or just collection. Everything in X is a collection, right? Otherwise we don't want to expand it. That works a little bit better. Collection of only collections. Which is more or less the predicate that the other solutions use. And let's see how we do. Does it still work? Yeah, it still works in these cases, and works in this case as well. All right, let's see it. Let's see it. Yep, there you go. But obviously it doesn't flatten these other collections at all, which is kind of interesting. But yeah, the other solutions that I saw do the same thing. They didn't really specify what to do in that case. If you read carefully, it doesn't really tell you what you should be doing. The other solutions just do like recursive mapcats. If the thing you're looking at, they do a similar predicate here. I could actually look at the solution and see. 94 is where we're at. Okay. Yeah, here we say if every one of these are these sequential. Oh, yeah, okay, they use the complement to go in the other direction. So if really it would be like this. If everything is sequential, then mapcat fx and you recurse. Otherwise, just return the thing as a single value in the set. Same difference, yeah. Simple idea, really simple. All right, let's go to 94. So yeah, by the way, what mine does, I don't know if I explained it. Basically, this tree sequence will do a depth first search. This will figure out whether or not the thing you're looking at is an inner node. If it is an inner node, it'll use this to on that node to generate the children, which obviously we can just use the identity because it's a sequence of children, right? So it just gives you the sequence itself. Those are the children, and it'll continue operating on each of the children. It'll recurse. On each of the children will perform this again and then perform this and sort of back and forth. And it creates a set of all of the nodes as you visit them, a sequence. And what you can do then is filter on that sequence and say, okay, if the thing I'm looking at is an inner node, just remove it, filter it out. So the column of only columns is what defines the inner node. And so if we take the complement of that, that means that we'll only have the leaves. And the leaves obviously are the sort of final it's the final sequence of these collections concatenated. Yeah. So, or just the leaves are just one level before breaking the sets down into elements So they're all just the smallest possible reducible collection in our original list of collections, which is exactly what we want. So this is, I like tree sequence. It's useful in some cases. Like for this problem, it's worked nicely. Mapped to this problem rather nicely. Let's get rid of these. We're not going to look at happy numbers right now, so we can just get rid of all that. Right, the game of life. Okay, so this took a while. I can talk about this. The deal with the game of life. So also considered hard. We did solve it. We'll describe the solution. It's kind of like, I don't know. This took a while, and the reason is just I'm kind of unfamiliar with Clojure and some of the mechanics of it all. Although I could have made the same mistakes whether or not it was Clojure. But let's look here. Game of Life is a cellular automaton devised by mathematician John Conway. Board. By the way, I made a website that uses the Game of Life kind of extensively. Not a website, but yeah, I guess a website. It's like a game, web app type game deal. Kind of a lot of different pieces of stuff going on in there. Not anything particularly, I want to say like worth bragging about, but it was cool. It was interesting putting that all together. So anyway, yeah, Game of Life, pretty neat. Cellular automaton, and let's read. So a board consists of both live and dead cells. Each cell interacts with its 8 neighbors, horizontal, vertical, diagonal, and its next state is dependent on the following rules. So there's some cellular automatons are pretty neat. Right, the Game of Life being one of them, and there's some rules that basically decide whether or not, like, it goes state by state, and there's sort of a board of live. Well, you'll just read it, just explain it. This explanation's pretty good. This is probably better than how I would explain it. Any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies as if by overcrowding. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. Write a function that accepts a board and returns a board representing the next generation of cells. So yeah, there's some pieces to this. So I did it really the really naive way, which is just for each living cell, or just each cell, you can find its neighbors. So you just check the 8 nearby cells that are also within bound. I usually do it as the 9 cells, not including the cell itself, and also the 9, sort of the square around that spot without including the spot itself, and then also just a predicate that checks if those things are in or not, or not in bounds on the board. And yeah, so here's the code. I'll just walk you through it. So it says live, dead, right? So this is, oops, don't do that. Clojure, you can use the syntax to get a character literal, and you have live, dead, m row, m column. Just count what's on the board and then just check if there is something in the board. This is just kind of like more like a sanity check. Well, not really a sanity check, but this is maybe a sanity check. And then you're gonna take the first of the board and count that. And then if it's, I guess, non-existent, then return 0. This could actually, I don't think you even need this. Because I think first will return nil if the thing is nil. So we can actually line REPL. I could show you what will happen. Yeah, let's see. If we take first of nil, I want to see what we end up with if we crash or whatnot, or what have you. Yeah. Yeah, okay. So actually we don't even need this. Yeah, it just returns. The if would, what if you do count of nil? Actually, hold on. Maybe I do need those. Give me a second here. I didn't think of that. So first of nil can give you nil, but what does count of nil give you? That might give you a problem. Oh, 0. Okay, good. That's perfect. So we don't need any of this. You could just count first of board. Okay. Again, we assume the board is for the most part well formed. It's n by n board. So inbound, live, dead. Inbound just means that we're greater than 0 but less than the number of rows, right? Actually, this should be greater than or equal to 0. I coded this incorrectly. Whoops. Oopsies. Live is if the character that we're looking for, and I used nth of nth. I think there's probably a way to get to this that's better. But the board was kind of input in a strange way where it's a sequence of strings. So you kind of need like it's a sequence of strings, so you kind of need like nth of nth. You could do things to manipulate this stuff if you don't want to do it this way, because this doesn't generalize too well to multiple like variadic number of dimensions for your board. If ever you wanted to do that, but it's okay for what we're working on, right? I mean, don't always need to write super generalizable code. Although that's best thing to do is to have it make it as generalizable as possible. But anyway, so right, you just check get what's at that the board at that spot. Check if it's alive by comparing it against the live character. Do the same thing with the dead character. And then live neighbors is going to perform what I was describing, where you take a range from -1 to 1, right, excluding 2. Also -1 to 1 for ij, except when I and j are equal to 0. Only when I and j are equal to 0, or not equal, but don't include I and j equals 0, right? So they'll give you eight things rather than 9 things. And then you just add to the row I, add to the row, add to the column j. Take that pair, right? Do this list comprehension over these 8 things. Basically, the spot surrounding your grid position of interest, and yeah, then filter on everything that's inbound, right? And then also filter on everything that's alive, and then count the number of things that are alive, and that should give you the number of live neighbors for a particular row column. Yeah, and right, and we abstracted away, right, the live and the dead. Keep it kind of simple, right? I like having kind of small helper functions like this to organize the code. I think it's useful. I think it's good. Right, so you count the number of live neighbors and using a list comprehension and this is called a threading macro. It basically just says take the result of this, push it into this, take the result of that, push it into that, take the result of that, push it into this. At the end, it'll be the last argument. Call this with this thing as the last argument here. And so so you can count the number of live neighbors with a single routine, and then you're going to go ahead and say, all right, given some position on the board, let's find the next state. What we're going to do is get the live neighbors from that position, and then perform a bunch of checks. Right, these are basically the rules. and well, that'll let us know whether or not it's dead or alive for the next position. And you could sort of doesn't take too much. This isn't too hard to figure out. What this con does is it's like a fall through. So it's not quite a switch statement, but it's similar. It's like a nested if else, more like it. You can't get all the way down if you terminate anywhere here, like you don't end up going all the way down, but you can't get to these bottom parts without first going through these. So yeah, think of it like a nested if else. Then yeah, so you can get the next state by first running the routine to get the number of live neighbors, and then all you've got to do is use another list comprehension and say, okay, for all of the rows, we're going to perform this operation, which has at its core another list comprehension over all the columns to get you sort of a sequence over a row of the characters. It's not even the characters over a row, just the indices for that, representing that row and column. Effectively, all the columns within a specific row, all of the iterate over the columns within a specific row, all those cells, and then you're gonna map to those results to each one. This next state, right? Create that sequence of what the next character should be for that particular cell for all the cells in that row. Then join all those things into a string, all those characters, and as we said before, we're doing that for every row. So you end up with each row has that sort of string, conjoined string of what the next state is for the things in that row. And then you create a vector out of all of that. And that should do the trick. Pretty simple, pretty easy, pretty straightforward. Kind of a lot of code and a lot of explaining, I guess, a lot of stuff going on. But it's really not bad at all. I mean, it's pretty simple overall. That's the thing. It's not really that tough. It's just a lot of pieces, I guess, small pieces. Like I said, it's like these are all like practice questions to like learn the syntax of the language, which is pretty good. Like I would say overall, they did a good job. Like it's kind of exactly the kind of stuff you should be doing to learn about the language. Excuse me, and see what other people do, how they kind of shape up their code a bit. I don't know if I looked at the solutions for this. Was that 94? It's almost an hour of just going over these problems. Yeah, I kind of don't like how other people do the ones that are a little more involved. Excuse me. I don't know. It just tends to be somewhat messy, but I shouldn't say that. I mean, it's all pretty similar. Anyway, I wouldn't really say. It's not really true. One better than the other. It's like it's arguable. All right, so let's go to the next one. So that was 94. Game of Life. 95 is to tree or not to tree. Oh, okay. So this is an interesting question. Basically, they asked, can you determine whether or not what you're looking at is a binary tree, meaning it has a value and then an input, left and a right, and the left and the right are either trees themselves or nil, right? That's kind of what it comes out. They didn't really explain that here, but if you look at the test cases, what passes and what fails, that's basically what it means. Nil represents an empty tree. It's like that's the terminating character for the left or right tree. So it's either another tree or it's nil. And so what makes it a tree is it has a value, has exactly 3 values. It's sequential, and it has a first value and then two trees to the right of it. So what I said was, okay, if the thing is sequential, then continue. If it's not sequential, then check if it's nil. If it's nil, return true. If it's not nil, then we don't have a tree. And then you're going to say, if the count of this tree is 3, then check that the the second value in this sort of tree node is a binary tree recursively, and then also check if the third value is a binary tree, as it represents the head of a binary tree recursively, and return that. Otherwise, right, if the thing doesn't have 3 values, it maybe has 2, it's malformed in some way, then just return false. And that seemed simple enough and seemed to do the trick as well. And there you go. And the solutions for this one, and this is easy, very kind of easy problem. The solutions, I don't know if I even looked at them, but they all had something similar. Yeah, no one really had like a super concise one. I usually like to check and see if there is one. Yeah, it was all kind of similar. Probably about the same thing that I had. Let's go to 96 now. Beauty of symmetry. Now this was a really cool question. So this one, this one was kind of involved, and I was impressed by the solution here. So it says, let us define a binary tree as symmetric if the left half of the tree is the mirror image of the right half of the tree. Write a predicate to determine whether or not a given binary tree is symmetric. Right. So, very interesting question. Easy. So what I did initially, and it's using the same tree representation as what we were using previously. So this is pretty interesting. What the solution, but what I ended up doing is I said, okay, it says it's easy, so it's got to be like a very concise way to do this. In order for a tree to be mirrored, what you've got to have, there's really two things. One is it's got to be the left tree and the right tree. The left tree is a mirror of the right tree. Which means, and then what does that mean? For the left tree to be a mirror of the right tree, subtree, it means that the head nodes match, and the left subtree of the left tree is a mirror of the right subtree of the right tree, and the right subtree of the left tree is a mirror of the left subtree of the right tree. Which is pretty confusing. But that's what I coded up initially, and that worked out nicely. I basically just wrote this routine that will recursively check if subtrees are mirrors of each other. And that's all well and good. It was correct. It worked. But it was kind of verbose, kind of ugly. Had required a bit of thinking because it wasn't so clean. And what it came down to is, alternatively, so you could check that. That's all well and good. Alternatively, you could reverse the tree recursively and check if the reversed tree is equivalent to the initial tree. Effectively mirror, reverse your tree, right? And the way that works is, I don't see that too often, so I didn't really have that like immediately ready in my repertoire, but now I probably will forever because it caught my attention. Basically what that comes down to is saying, okay, destructure your tree into 3 values, three variables, right? The first variable being the value of the node itself, and the other 2 being the subtrees, right? The left subtree and the right subtree. And what you're going to do is left subtree, right subtree, what you're going to do is, whoa. Yeah, destructure into 3 values, right? The three things, the value of the node and the left subtree and the right subtree. And what you're going to do is yawn first because you're very tired and ready for bed. It's been a long day. The left subtree is, what the heck am I saying here? Thinking. Left subtree, right subtree, node. Right. Sorry. So you destructure into 3 variables: the value of the node, the left subtree, and the right subtree. And then what you're going to do is you're going to recursively reverse the left subtree and the right subtree, and you're going to swap their positions. Right. So that's what the reversing is going to do. You're going to take both those subtrees, reverse them recursively, and swap their positions. And obviously the sort of the next, you can imagine the next level down, because it's the same node, it should be the same node, doesn't really do anything. But because you've now swapped these positions and you go to the next level again, you realize that the 2 subtrees of each of those subtrees will then get swapped also and reversed. And so you have this reversing going on, sort of alternating through the tree. As it turns out, that's exactly what the mirroring does. When you mirror one tree to the other, it's basically this kind of recursive reversal, which I haven't really been able to like fully articulate or understand. Like, why is it that if you mirror one subtree to the other, or just flip, quote unquote, flip those subtrees, it actually has the same effect as this recursive reversal. I don't really fully understand it. I don't really know why. An alternative way to understand this is that you've reversed at every depth, whatever the nodes are, you've reversed the order of those nodes and every single one of them, at every depth. That's maybe another sort of rationale for calling this recursive reversal a actual reversing of the tree. But yeah, that's basically it. You effectively mirror the tree, and check that the original is equal to the mirrored version. Something like mirror around the mirror the tree around the midpoint. Well, really, it's reverse everything. Yeah, reverse each depth. And if it's still equal, then that means you were appropriately mirrored. It means that every depth of every vector of every sequence of nodes at a given depth was palindromic to begin with, if the reversal is the same as the original. Pretty interesting. Definitely interesting question. We consider it an easy problem. And there you go. The code is just that, right? So you destructure your tree into left to right and the node value. Check if it's nil to end the recursion. And if it's nil, return nil. Otherwise, return the subtree. Otherwise, return the tree as the same value. Head doesn't change, but the 2 subtree positions get swapped and they're operated on recursively. Pretty cool. Pretty cool. I was really impressed by that. I mean, it seems kind of simple, but definitely caught my attention. Definitely caught my attention. Let me we'll continue here. Oh, what happened? Where'd it go? Ah, it did go. Fell in my hoodie. Okay. So let's take a look at 97 now. Oh, didn't mean to. Pascal's triangle. Oh yeah, this is a pretty easy question too. I've seen this enough to like kind of know this one by heart by now. And also I was able to use Clojure's language to sort of do this quickly. So Pascal's triangle, the triangle of numbers computed using the following rules. The first row is 1. Excuse me, each successive row is computed by adding together adjacent numbers in the row above and adding a 1 to the beginning of an end of the row. Write a function which returns the nth row of Pascal's triangle. So real simple brute force. We just sort of a dynamic programming, layer by layer, perform exactly that. Start with a 1, loop over a range from 1 to n, not including n, and obviously not including 0. We don't actually care what's in that range, so our reduction is just basically leaves that value out. Reduce over this function is where the magic is going to happen. Start with x's, we'll say, starting at 1, and you're going to map the previous whatever you got with a new set that has one less element, right? This is the shifting that I described earlier. Map over that, add all these numbers. Notice that you end up without the first and the last, and so you concatenate those ones on the side. So you'll end up adding, for 1, you end up adding 1 and nothing, which is just nothing. So then you just end up with 1 and 1 concatenated. And then the next iteration you say, let's do 1, 1 as one vector, and then the next vector is just another 1. So you have 2 and you have just 2, right? Ends up with just 2, and then you add 1 and 1 on the side, so you get 1, 2, 1. And then the next thing you have 1, 2, 1, and 2 1s. You end up with 3, 3, and add the 2 1s, get 1, 3, 3, 1, and keep going in that fashion. And yeah, that seemed to work out nicely. So not too bad. Kind of, not that you can't do better than this, but this is pretty good. There's a few variations of this. I like the concatenating one. That was the best. I had something else first. We had like a cons and conjoin in there, but the concat is just cleaner, simpler. Yeah, so that's Pascal's triangle. Fair enough. Let's go to 98. If we have that. And I think we'll read this one and then I'm going to bed. So this is where I stopped. Have another, still have 58 problems, I think, left to solve. So there's still a lot of work to do here, but we're making pretty good progress here, pretty good headway. I think it's been a few weeks now we've been on this. So we're, getting familiar with Clojure. I'd say at this point, I'm like pretty good as far as like understanding the syntax and like the basic stuff. There's a boatload of different, what do they call that? Like manipulations, built-ins, things you can use, but getting pretty comfortable with it by now after almost 100 problems. Well, yeah, actually over 100, right? Because we solved some HackerRank problems already. Maybe I should try writing some of the hard HackerRank problems in Clojure as well. Try a couple of those. I noticed that my channel has been steadily gaining views on the hard LeetCode problems. I thought that was interesting. Yeah, I could upload more of those, a few more of those. Anyway, so a function f defined on a domain D induces an equivalence relation on D as follows. A is equivalent to B with respect to f if and only if f of A is equal to f of B. Write a function with arguments f and D that computes the equivalence class of D with respect to f. So this is kind of neat. This is like creates sort of like a partition. Equivalence classes, that's kind of you basically, if you have a proper equivalence, if you have a proper partition, then you have proper equivalence classes. I think, I want to say that you don't have equivalence classes without a partition, and you don't have a partition without equivalence classes. Basically like something like that. Something like that. I don't know. I mean, I guess in theory you could have something like an equivalence class without partitioning the entire set. But that's kind of weird. I don't know. I think I usually don't think of it that way. Anyway, so what they're saying is, we'll read it again. So, function f defined on a domain D induces an equivalence relation on D as follows: A is equivalent to B with respect to f, if and only if f of A is equal to f of B. So, like, the equivalence, the go-to equivalence class and/or partition is the modulo functions. Basically, if you take something and subtract, like let's say it's modulo 3, subtract 3 from it repeatedly until it's in a range, or add 3 repeatedly, whatever you need to do, add or subtract 3 repeatedly until the value you're looking at is in the range between 0 and 3. Between 0, 1, or 2. It's between 0 and 3, including 0 and not including 3. Otherwise known as the divisor. When you divide and you have a remainder, the remainder is the modulo. That's sort of where the modulo function comes from. Now the deal is, so basically modulo operators create equivalence classes, right? So the entire natural number set there's a set of things that are equivalent to 0, a set of things that are equivalent to 1, set of equivalent things that are equivalent to 2 when you're dealing with like the integers modulo 3. That's like one of my favorite partitions and favorite sort of classical example of like what it's like really iconic equivalence class, equivalence relation, equivalence class is basically the classes would be everything related to 0 is a class, everything related to 1 is a class, everything related to 2, is a class, or everything equivalent under modulo 3. So, okay, so if and only if f of A is equal to f of B, write a function with arguments f and d that computes the equivalence classes of D with respect to f. So they give you the domain. How do they give you the domain, though? Well, what you can do, assuming that the domain is finite and relatively small, you could just operate f on every D and you'll get results, and you would say all of the values, you basically would use the result as a key in a hash map, and then you would add the result, you would add what got you that key to a set hashed at that value. That makes sense. You could do a simple reduction to do this over the domain. Now the problem with that, though, is like modulo function is kind of confusing because actually they even did it in the modulo 3 here. Why? Oh, I guess the domain is just a set. Yeah, okay, then you can. In this case, I could probably just code this up before I go to bed. Oh, constantly true. Oh, that's interesting. It's just always true. Yeah, you would do something like, I probably could just code it right here. Say equivalence class, domain D, this is predicate, and we have, function, predicate, right? And we want to say, a reduction reduce. We have this hash map we've got, and then we're also going to get the values after we're done. We're going to say there's the domain we're going to operate over. We've got these function. We've got this ret, and there is. I could just take the value, and we get this key, which I suppose we should calculate the key once. So we'll even put a let in there. Just call the key function or predicate of v, right? And then we're going to go ahead and return. We want to associate with ret on the key k, and we're going to use get, or we can just ret of key, and then the default. If it's nothing there, then we have this set we return. And we're going to associate this, we're going to conjoin into this set whatever this value, not the value, but the key itself. No, not the key. Yeah, the value that okay, yeah. So, realize that's confusing, but, right. So, we get this key, and we say, okay, whatever is already there at ret for that key, get it. If there's nothing there, then we get an empty set. Then we're going to conjoin v, which is the thing that we operated on to get this key in the first place, right? So if this was like 5 modulo 3, the 5 would be the v, right? And so now this v is going to get pushed into 5 modulo 3 is 2. It's going to be pushed at key 2 into the set. And then, right, so we perform this. Let me get here. So we have this conj here. We have this association here, associate here. And then we have this let, and then finally the function. There's a bunch of different pieces to consider. So conj, associate, let, boom, and then function, and then the reduce will be over d, and then we get these vals, and this probably should be in a set even. I think that ought to do the trick. Let's see if that works. There we go, done. Easy peasy. If that was an interview question, I would be all over it. So, all right, let's get the next one then we'll go to bed. Product digits, easy. Write a function which multiplies 2 numbers and returns the result as a sequence of its digits. Oh, that's interesting. Oh, there's a few ways to do this. You could just do a simple multiply the 2 and then get the digits, parse the digits, which I don't particularly like parsing the digits in Clojure. It's not so clean. Probably would write like a subroutine to do that, and probably write it iteratively because, like I said, it's not super clean. I mean, it's clean enough, I guess. You could just get the digits of the result. It's probably what I'll end up doing, I guess. Yeah, okay, simple enough. The alternative is you could multiply you could perform the multiplication algorithm, right? Which is take the first 2 values, multiply them look them up in the multiplication table, right? Like 9 by 9 will give you 81, and then that gives you a number, and then you're going to add that number to the next result. But the next result, would be because you're shifted over a digit, let's say you do 9 and 90, you actually end up doing all the way across one sequence with the first digit of the other sequence, right? That gives you a bunch of stuff. You add that all together. Then you do the second digit of the second sequence against all the digits of the first sequence with every result shifted by 10, multiplied by 10. So you'd have 10 plus 10 times that result, and then you do the next result, and so on. And so you could in theory perform the actual multiplication algorithm you know, sequentially, but I don't want to do that. Don't have to do that. I don't want to do that. We'll come back to this problem. We'll probably just parse the digits after you could do also really simple, like to keep this really concise, you could do a map the digit to a string and then map over that string, map each to a, you can use the Java like string to character, or yeah, string to integer, or parse int function. So you can map string, map parse int, and that'll give you the digits as a sequence, and I guess parse that into a vector. That works too. That's simple enough. I might try writing that when I come back. Yeah, let me go. So thank you for watching. Do appreciate it. Talk to you soon. Have a good rest of your day. Good night. And yeah, we'll just keep going tomorrow. We'll just keep going. You know, get familiar with Clojure. Get familiar. That's the plan. And I don't know what I want to do. Well, no, I have some ideas what I want to do. There's a bunch of things I want to do. We're done with this, but start with that. Just start with that. You know, we got our what we're doing mapped out here. So yeah, take care. Tomorrow I think we'll do. Oh, not tomorrow. Sunday we'll do some evangelizing stuff. Maybe a few hours on Twitch. We'll just read the Bible. Read the Bible. Hallelujah. Take care.